Hello guys, this is Paul McWhorter with TopTechBoy.com and we're here today to rumble. Let's see, I will need you to pour yourself a nice tall glass of ice cold coffee. That would be straight up black coffee poured over ice, no sugar, no sweeteners, none needed. And you guys go ahead and do a check-in in the live chat and I'll give you a shout out. I see that we've got BBF in the house. Arnold, hello. Larry, let's see who else we have. Adam, Luis, Lee, welcome. Okay, guys, we are going to be talking about the state machine today. And as we're doing a little chatting, if you guys want to play along at home on your Raspberry Pi Pico W, go ahead and put an LED, connect an LED and current limiting resistor to pins 16, 17, 18, 19. So while we go through some of this introductory banter, you guys could go ahead and be getting your circuit hooked up. Okay, Lee is here. Hey, Wise Ninja, it's been a while. I haven't heard from you in a while. Welcome back. Trickman, welcome. Daryl, hello. ADHD Acres, okay, welcome. Great to have you. Man, I'll tell you guys, I have been up since 4 in the morning. So I showed you my iced coffee, but I have like a whole lineup of coffee this morning. If you want to see my coffee lineup, let me know in the chat. Maybe I'll show you the full spectrum of beverages that I have this morning, okay? Yeah, Wise Ninja, you've been a long time guy here, so we appreciate having you back. And Chris B, welcome. Nice to have you there. Josh, welcome. Okay, we've got a nice group forming here. James, okay, might need a gallon of coffee. Okay, well, if you want to see my coffee lineup, leave a little comment and I will do it. Hey, Catherick, Michael, Larry B. Great to have you back, Larry. Haven't heard from you in a little while, so it's great to see you here. Abd Arlman, I'm sorry if I'm not saying that right. Davey, Jason M. Okay, we've got some people coming in here. That is nice. That is nice. VJ, hey, VJ, nice to have you live today. Appreciate all your comments on the channel. Okay, let me show you what we got here. Back behind me, we have a picture of dawn breaking over the headwaters of the Nile. Hey, VT, welcome. Rogo Bill, finished the Arduino. Great, BBF. Okay, love you guys. You can see, let me get out of your way, that we have dawn breaking over the source of the Nile live back behind me. So as we enjoy our coffee this morning, you guys can kind of watch the sunrise over the mighty river Nile. Okay, let's take a look at what my coffee lineup is this morning. You guys got to remember, I've been up since before 4 o'clock, probably about 3:30 this morning. I got up to try to get ready for this live stream. And so I did put together a nice set of coffee. Right here, what we have is we have my traditional morning drink, which is a half cup of cream, half cup of heavy cream that is foamed, and then 3 shots of espresso in it. This is a flat white, 2 shots of espresso. This is my traditional iced coffee that I usually drink when I am teaching, and then this is a macchiato. So I'm hoping that this morning I will not run short of coffee, because when you get up at 3 in the morning, no, the one thing that you don't want to do is you don't want to run out of coffee. So I'll probably finish up this creamy cappuccino, because I've been working on this since very early this morning. So I'll probably finish this one up and then I'll start hitting some of those other beverages. Okay, so it looks like we've got a nice group of people here today. And what are we going to be talking about? We are going to be talking about the Raspberry Pi Pico state machines. Okay, what are the state machines? The Raspberry Pi Pico has 8 state machines. And what you could think of a state machine is, it's almost like a separate little core off to the side, but it's a very crude core. It doesn't do very much, but it runs very much completely separately from your 2 main cores. And so you've got this extra hardware out to the side that you can utilize. Now, there's been some discussions about, oh, you can do state machines on the Arduino and things like that. But what you have to see is that a state machine in its very essence is separate hardware, dedicated hardware. This set of transistors over to the side of your chip that is specifically designed state machines. Now, if you are simulating state machines on your main core processors, That's not the same thing at all, because you're sharing resources between the operating system and your interpreter or compiler and your timing and your code and all that. It's all sharing the resources. The thing about a state machine is it is totally separate hardware that is dedicated to doing nothing but the specific job that you have given it. And so that is what is special about it. And what we are going to do is we're going to write our first program today so you can sort of see how do you access those 8 state machines. How do you take advantage of them in your programs? Okay, let me jump in. Let's see if we've got any. Yeah, Jason says I've got a lot of coffee. No, I'm not going to be jittery. It's going to get me in my zone here, I promise you. So let me see if I can come over here and let me see if I can kind of draw for you what the state machines are doing. Okay, what language is the state machine written in? Well, really what I would say is it's kind of assembly. We're going to be programming in something that is very much akin to assembly, but we're going to be interacting with the state machines through Python, but it's not Python code. We are going to compile assembly code. We're going to send it down into the state machines, and then Python is just sitting there on its own. Python then doesn't really have anything to do with anything at that point. Okay, let's say goodbye to the now, and let's come over to the Sketchpad. And I guess what I should say first of all, though, is that the kind of like in the title, why the state machines are so important. Okay, now if you think about our Raspberry Pi Pico W, it will run really fast. It will run at 133 megahertz, 133 million hertz. That's very, very fast. And that's plenty fast enough for anything that we would want to do. But the problem is, even though it can run very, very fast, it cannot run very, very exactly as far as time goes. So let me give you an example. I was writing some code to work with the little ultrasonic sensor. And what the ultrasonic sensor wants to see is it wants to see a 10 microsecond pulse. Well, if I can operate at 133 megahertz, there's no problem generating a 10 microsecond pulse. When you generate that pulse, it then sends a ping out, it sends a pin high, and it keeps that pin high until it sees the ping come back, and then it sends that ping low. So what do I need to do? I need to exactly create a 10 microsecond pulse, and then I need to listen and measure the amount of time that that pin on the ultrasonic sensor is high. So that's very, very precise timing. I write the program, it looks like everything's working fine, but then when I put it on the scope, the oscilloscope, I see that even though I told the Pico to make a 10 microsecond pulse, I really got a pulse that was anywhere between 40 and 65 microseconds. Now, what is the problem? The problem is I am working on that main core, that main Pi Pico core. In that core, every line of code is written in Python. Every time it has to be interpreted or changed into actual machine code, and then the machine code is executed. And then as I'm going from step to step to step, Python might decide something like, oh, it's time to clear the registers, or it is time to do some memory management, or check this or check that. So there's all these like background processes that are going on that will totally mess up your timing. So anything that you're trying to do that involves precise timing, you just simply cannot do it in Python on the main core, because that main core has so many different things that it's doing. You can't do precise timing. So what can you do? You can go over and you can put code in those state machines, and they don't do anything except exactly what you tell them to do. It's like you're going down and you're starting to operate at the bare silicon levels. You're starting to interact with those transistors on the piece of silicon. There's nothing between you and the transistors. Okay, I hope that sounds a little bit. Sounds a little bit exciting to you. I am really enjoying it. Okay, hopefully you guys are getting me okay here. Let's see. All right, we've got some. some things here. Okay, so let me come over here. You can see that the dawn continues to break. Dawn continues to break over the Nile. But let's come over here and let's talk about these state machines. All right, so let me see if I can kind of draw for you what is going on. Okay, so what we have is, what we know about is, we know that in Python, what I have is, I have trouble getting my sketchpad to work. What we know in Python is that I have, I'll get this, guys, there it is. I have a core. I have a first core in the Raspberry Pi Pico W, and I have a second core. So what is this? This is core 1, and this is core 2. You guys are familiar with that if you have taken my class, right? Because we have talked about those. We have talked about those two cores. Now, what do we do in this core? I can write a Python program. Now, how do I take advantage of the second core? Well, usually what I do is I create there a Python thread. Okay, so with good old-fashioned Python programming, I can utilize both of those cores, those independent cores, I can utilize using Python. So over here, I have core 1, core 2, I have a Python program, and I have a Python thread, and I can do that. We have already worked with that. But what we also have that we really haven't talked about, there is a programmable input-output block. There is a programmable input-output block, and there are two of them. Now, I'm not trying to suggest that the top one is associated with core 1 or the bottom one is associated with core 2, but there are two PIO blocks. So what will we call this? We will call this PIO1, and we will call this PIO2. Now that's for programmable input-output, PIO1, PIO2. Now what does each one of those PIO blocks have? Each one of those PIO blocks has 4 state machines. So what I could do is I could say this is 1, 2, and then I've got 3, and then I've got 4, and then I've got 5, 6, 7, 8. Okay, so what I've got is 8 state machines. Each state machine is like a very simple, crude core. You can write a program and you can download it into state machine 0. You can download it into state machine 1, state machine 2, state machine 3, state machine 4, state machine 5, state machine 6, state machine 7. Since I started counting at 0, that's 8 state machines. So I can have, besides the program on the main core and core 2, I can have simple little assembly language programs running on these different cores. Okay, that is pretty amazing. But now this is the big picture, but let's just think of, I'm going to make it as simple as possible for today's lesson. Let's think of one core with one Python program working with one state machine, and let's see how that would look. Okay, and so I will go ahead and clear this, and so what we'll do is we'll come in, and what I'm going to do here is this is having a little trouble drawing today. There it is. Okay, what is this? This is core 1. Okay, and what do I have on core 1? I have a Python program. Okay, now what do I have over here? I have one of the 8 state machines. Okay, so this is my state machine. So we have the Python program, then over here we have, let's say this is state machine 0. Now what you have to see is the core is one set of transistors on the silicon. The state machine is a second set of transistors on the silicon. This is totally separate hardware that just happens to be on the same chip. Okay, it happens to be on the same chip. Now, how do these things talk to each other? How do these things talk to each other? How does my Python program talk to my state machine? Well, there are two first in, first out registers. Okay, two first in, first out registers. And each register has the ability to hold 4 words. What is a word? It is 32 bits. That's 32 zeros or ones, not bytes, but bits. 32 zeros and ones, and we can have 4 words. And so I can go like 1, 2, 3, 4, 1, 2, 3, 4. Now, what I can do is, these are first in, first out. So you see it can hold 4 words, but whatever I put in first will be taken out first. And so how can I get data from my core, from my Python program into the state machine? Well, I can send it through a put command. I can send it through a put command to this first in, first out register, and this is the TX register. Okay, this is the TX register, and this one is the RX register. So I can transmit to this, and then inside the state machine we have 4 different registers. So let's see if I can draw out those 4 registers. And this will make sense because we're going to start programming this in a minute, and you can see how the code does these things that I'm trying to show you. Okay, you'll see how the code does these things that I'm trying to show you. So I can put data into the FIFO TX, okay, from Python, and then I can get it. I can come over here, and what this is this is the output shift register, and this is the input shift register, and this is the X register, and this is the Y register. So I can put data from Python into one of these slots in the FIFO TX register. And then how do I get it into the state machine? I pull it. Okay, so pull is a state machine command. Put is a Python command. So Python puts it into the FIFO RX, and then the state machine pulls it into the state machine into the OSR register. Then what I also can do is I can take data in the input shift register, and I can push it, and I push it back to the RX FIFO register, and then from there it comes over here, and I can get it back to Python. So what can Python do? How does Python interact with the state machine? It can put data to the TX shift register, and it can get data from the RX shift register. How does the state machine interact with those shift registers? By pulling data from them or pushing data to them. Okay, and then what we can do is this state machine, it can send data or receive data from the GPIO pins. Okay, it can send data to the GPIO pins, or it can get data from the GPIO pins. So what can we do in the FIFO, TX, and RX? We can have 4 words, and each word is 32 bits, a string of 32 zeros and ones. All right, 32 zeros and ones. And we can have 4 of those. So I can put 4 times. But before I put another one, I better pull it or I'll overflow. So you can have up to 4 words at a time that are sort of sitting in the queue. Okay, so now what can I do as far as writing a program for the state machine? There's a couple of things that you need to know. There are only 8 commands. Okay, how many commands do we have in Python? You got thousands and thousands and thousands of different things you can do in Python. Hey, come here. What?
Are you talking?
Yes, I'm talking. Look who this is. You guys know who this is? I don't think I've introduced him. Can you say hi? Yeah, this is Paul McWhorter 2.0, and he's up early this morning coming in to say hi. Do you like working on circuits?
Yeah.
What did you build?
A socket.
Yeah, you built a circuit. Okay, little man, I'm teaching, so you're going to have to go, okay? Go find Miss Nana. All right. Sorry about that. Wasn't expecting him to. Yes. Okay, you got to go, little man. All right. Okay, so anyway, that's my grandson, and he sits here and he works on circuits with me. Okay, so there are 8 commands. There are 8 commands that we can use in the, there are 8 commands that we can, I am teaching, sir, yes. Oh, okay, thank you, I appreciate that. Okay, so there are 8 commands, and they are machine language commands that we can use in the state machine, and they're pretty simple. I can bring something in, I can send something out, I can push, okay, I can pull, I can move, I can set an interrupt, or I can jump. Those are the 8 commands. Now, you see there are no commands like add, subtract, multiply, divide. There's no commands like exponentials or logarithms. There's nothing like that. It's just these 8 very, very simple commands. Hey, Andrew. Great to see you. It's been a while. Haven't seen you, haven't heard from you in a long time. Welcome. Hopefully you're doing well, and hopefully we'll see more of you around here. Again, we miss you on the channel. So you have 8 commands in assembly language and machine language that you can use on the state machine. So you've got to really start thinking. There's incredible things you can do, but you've got to be creative, and you have to be very thoughtful in creating creative ways to do complicated things when you only have 8 commands. Now, not only do you only have 8 commands, the program can only be 32 lines of code. So in a state machine, the program can't be more than 32 lines, and each line can only be one 32-bit word. So if you look at the whole program is like 900 bits, something like that. You've got 32 lines, and you have each line can have 32 bits. You see, I hope that what you see here is that we're really getting down to working with zeros and ones. We're really getting down to operating at the bare silicon level. And you say, well, I can't do anything with these 8 commands. Well, you can. You just got to be very clever. What is the power? When I come over, what is the real power of this? When I come over to work with this state machine, I have absolute control over the timing and over what happens. So if I say for pin 7 to go high, pin 7 goes high, and then if I say wait 1 clock cycle and then pin 7 go low, it does it exactly, precisely 1 operation per clock cycle, and there's none of this invisible overhead stuff that is coming between you and the silicon. Okay, guys, I have done way too much talking. And so let's see if we can take some questions here, all right? Let's see if we can take some questions. You guys, let me know. I've done a lot of talking, and let me know if you are aware of these state machines, if you're interested in them. Let me know if I've conveyed to you, you only see 7 commands. 1, 2, 3, 4, 5, 6, 7. Which one did I miss? Jump. Let's see. I think wait. There's also a wait. Okay, so there was one more that I didn't put in there. Good catch, Peter. I think the other command is wait, and so that is what we can do. Okay, you guys, I'm going to give you a second. Look, it's really looking beautiful out there. It's still dark enough that the color hasn't come on. Okay, Wise Ninja is interested. Okay, Peter caught that there's only 7 commands, but let's get some comments in here. Let's get some questions, and then what I want to do is I want to go ahead and sort of write our first little state machine program so you'll see how it works. And then on my Raspberry Pi Pico class, the next 7 or 8 lessons are going to be on the state machine. It's really like a new thing, so I'm going to take it slow and easy, and I hope if you go through those lessons you'll find that they're fun and that they are pretty straightforward to understand. But I get a little nervous because I'm not seeing any questions come in, which makes me wonder, did I do a topic here that absolutely no one is interested? Yeah, you could do a lot in the background, and that is exactly right. You are working in the background. Python can be doing all of its big and glorious stuff, and a state machine can take care of like the interaction with the component that requires precise timing, or setting up something that would be like PWM signals, things that require uninterrupted exact timing you do on the state machines. Sounds meaningful for an encoder. Yes, Davey, an encoder would be a very, very excellent thing that you could do with this. So that would be a good example. Okay, guys, and what I am going to be doing here up next is I have got 4 LED, and they are connected through 220 ohm resistors, and then I have it connected to pins 16, 17, 18, and 19. If you don't have time to do that, at least hook up the one on pin 16. Okay, at least hook up 1 LED on pin 16. Okay, Adam is interested but doesn't know what to expect. Maybe a few like me trying to make in the machine before I ask questions. Okay, I see. That makes a lot of sense. All right, so this is the circuit. Now today I'm not going to be using the buttons, but remember I said that you could send data to the GPIO pins, or you could read data from the GPIO pins, and so you could see that in future lessons we'll be using those buttons. No questions for me. I'm geeking out a bit watching Paul live. I'm not even on this series. Okay, well, Jason, you need to get on the Pi Pico series. I am just, every time I use the Pi Pico, I am loving it more and more. Can we go through those commands again? Okay. I'm not going to go through the commands because I can't really explain them. I guess what I would say is, let me see if I can come over here. Let me come back over here. What I guess I could say is, like, let's just think of the move command. Okay, let's think of the move command. And what you could see is I could get a piece of data. I could put it from Python into the FIFO. Then from the FIFO, I could pull it into the OSR. From the OSR, I could move it to the X register. I could move it from X to Y. I could move it from Y to OSR. From OSR, I could move it from ISR to OSR. From OSR, I could move it to Y, and then from Y, I could send it out to the GPIO pins. Or I could read something from the GPIO pins into Y, up to X, down to ISR, over to RX, and then I could get it in Python. So you see, you can just send data around, and then if you're clever with these commands, you can actually start doing things much more sophisticated than what you really think that you would you would really just at first glance think that you would be able to do. Okay, so let's come over here and let's start talking about how we would code these things, okay? And I'll try to keep my eyes on the comments in case some comments come up. Well, we're going to be working with a GPIO pin, so I'm going to say from machine import pin, from machine import pin. I think I'll have a sip of the flat white. Oh yeah, that's good. That's good. Still got a little of this one left. Okay, so from machine import pin. Now we're going to work with the state machines. So I'm going to say from RP2. That is the library that allows me to interact with the state machines. I'm going to import PIO, which is the method that opens up those PIO blocks that I didn't really show you too much about, but they're transparent. You work from Python to state machine, so you really don't have to worry about those PIO blocks. And then the method state machine, like that, and then the ASM underscore PIO for programmable input output. Those are the three methods that we need for that library. Okay, we might do a delay down in the main Python program, so I'm going to go ahead and say from time import sleep, just because we might do that. All right. Now, how do we create an instance, or how do we instantiate the state machine? You might think of it as initializing the state machine. Now, what's complicated is there's like two different commands you have to have, and you sort of initialize half of it in one command and the other half of it in the other command. So I got to kind of show you very precisely. So this is how you actually create a state machine. I'm going to call mine state machine 0. You could call yours whatever you wanted to, but my state machine, I'm going to call state machine 0. And that's going to be equal to that method state machine that we imported. Now, there are how many state machines? 8. Which one do I want to use? I want to use state machine 0. I could use 0 through 7. Okay, but I'm going to use state machine 0. And then where am I going to put the state machine code? The state machine code I'm going to put in my blink. So Python is going to know to look at my blink to get the machine code that will then be compiled and will be sent down into the state machine as a bunch of zeros and ones. But I got to tell it, where is that code? That code will be at my blink. Now, I've got to set the frequency of the state machine. Now, the slowest you can go is about 2,000 hertz. You could go up to like 100 megahertz. But if we're going to be blinking an LED, we're going to want to go kind of like as slow as we can. So hopefully we can see it. So we're going to set the frequency to 2,000. And now we've got to kind of give it an idea of how we're going to access the GPIO pins. Well, what I can do is I can say my out base, my base pin is equal to pin 16. Okay. Now, what you're going to notice is I can't say, oh, I want pin 16 as an input and I want pin 19 as an output and I want to come over here to pin 23. No, I'm able to set my base reference pin as pin 16 full stop. That's it. Now, can you work with more than one pin? Yes, but you can't do it the way that you think you would do it. So I have now instantiated my state machine. Now I got to come up here and I've got to do the other little things that are needed. And what I do is I put this @ symbol. That @ symbol gives Python a heads up. That @ gives Python a heads up that machine code for the state machine is incoming. Get ready, Python. This isn't Python code. I'm fixing to give you the code that you will compile and send down as zeros and ones into the state machine. What is that? It's at ASM underscore PIO. All right. And then I've got to do an out underscore init. Out, what is that out base that we said? It's pin 16. And what do we want to do with pin 16? Well, initially, I'm going to say RP2, the library, PIO, the method, and then out low. Okay, what does this mean when the state machine starts? It is going to set pin 16 low. So when it starts, I don't end up with it in an unknown state. I explicitly say, when you start running, I want pin 16 to be low. But what is this nonsense over here that I actually have 4 LED? Well, what I can do is I can come over here and I can put an open parenthesis, and then I can put a very awkward trailing comma, and then I can close that parenthesis and say times 4. So what I'm saying is I'm going to be working with 4 GPIO pins. When the state machine starts, I want them all to be low. And what will those pins be? Well, my base pin is 16. then by definition, and you can't change this, the other ones would be 17, 18, 19. 16, 17, 18, 19. Okay, those will be the 4 pins. Why? Because I have the base pin is 16, and then when I say use 4 pins, then it just uses the next 3 sequentially. Okay, so now with one command, now we've got 4 pins instead of 1 pin. Now, this is just something you have to do. I'm going to set the out shifter, and that's going to be equal to PIO dot shift underscore right, shift underscore right. Okay, out shift direction, PIO shift right. And so this is just saying the direction that you're going to be moving the data. And I don't want to take 30 minutes to explain it, but just believe me, if you say left, none of what I'm going to show you here is going to work. So we're shifting right, okay? And so I'll get back to the questions in a minute, but I'm just going to keep going. Okay, so now I have defined my state machine here. I've given Python a heads up that we've got the code coming now. And now what am I going to do? I am going to define right here, define my blink. Now that looks kind of like a Python definition of a function, but now the commands that I can put here are of those 8 commands that I showed you. And now I remember the command that I didn't put. The command that I didn't put in the 7 that Peter notices, the command was set. Okay, the command was set. All right, so I realize now that was the missing one. Okay, so now, where are we now? We're going to define the machine code. Well, what I do is I got to put a wrap target, okay? And what is wrap target? This is like, think of the void loop. This is going to be your loop, and this is going to be where your loop starts at wrap target. This is not a command. This is just a pointer, like this is where the program starts. And then when you get to the end of the program, you tell it to wrap. Wrap is not a command. Wrap target is not a command. It's like a pointer. When you get to wrap, it'll jump back up to wrap target. So what we've done is we've created a loop. Okay, now what I'm going to do, I'm going to set the X register to 0B. That means bits. I'm going to be sending it bits, zeros and ones. So 0B is a data type to send bits. So now what can I send? Zeros and ones. Well, how many LED do I have? 4. So how many bits should I set? 4. So I'm going to set it to 0, 0, 0, 1, like that. All right. Now, what can I do? 0001 went where? To the X register. Remember my state machine? I just dumped into the X register the binary number 0001. Okay, now what can I do? I can move to my pins from X. So whatever is in X, I'm going to move to my pins. And then what am I going to do? I'm going to wrap. All right. Now, somebody tell me what this is going to do. I got to make sure that's there. Somebody tell me what this is going to do. I'm going to be watching the comments now. Somebody tell me what this is going to do when I run it. Okay. Not sure. Okay, can state machine be used to catch asynchronous data input similar to how interrupt requests? Yeah, anything of that type is stuff that you would want to do in the state machines. So somebody tell me error. Okay, why do you think I'm going to have an error? What did I do? Did you find an error? Where is my error? You got from, not from line 3. I'm not sure. Okay. Oh, form. Okay, yeah, good. From. I did not see from. Okay, so anybody else, tell me what this is going to do when I run it. Any ideas? Okay. Any ideas? I think maybe there's a little more delay today than normal, so I'm not getting the comments coming in as quick as I would expect. But I want to see if anybody can tell me what they think this is going to do. Thank you, Shabru. That's very nice. Okay, well, let's just run it. And what you might think is I put 0001 into X, and then I moved X to the pins. I might think that that would turn the LEDs on. So let's go ahead and let's run this and see, shift direction out, shift direction. What did I do there? Out, shift. That sure looks right. For out underscore sift. Shift. All right, that one scared me. Okay, so let's try it again. And it ran this time, but absolutely nothing happened on the LED. Why did nothing happen on the LED? Well, I defined a state machine. I told Python, state machine code is coming. I gave it the state machine code. It compiled it. It downloaded it, but I never ran the state machine code. So how do I do that? I come over here and I have to say my state machine 0. Right now, what am I? I am locked and I am loaded, but I haven't pulled the trigger. The code is in the state machine, but I have to what? I have to do a sm0.active. In fact, I can't help but wonder, what if I did it down here, sm0.active, and then what if I turn that state machine on? I don't know if you can do it after the Python program finishes. Okay, I guess you can't do that, no, because the program finished. So what I can do up here is state machine active, and then I'm going to turn that on. Okay, so when I get to this line of code, I'm going to turn the state machine code on. So let's run this and see what happens. Okay, and still it didn't come on. Now that is very perplexing. Set x to 0, b 0, 0, 1, move pins, move to pins. That should have been pins instead of pin. And so let's try that now, and boom. Okay, man, that scared me. It should have been pins. And you see, one of the things is you don't get error messages from the state machine. So if you make a mistake, it is going to stay there as a mistake. So you see, I was able to turn that on like that. Now, let's try. What if we went 0, 0, 0, 0 like that? And what if we ran that? Okay, boom. You see what it did? It turned those off. Well, what if I came in and said, I want to set x to 0, 1, 0, 1, like that, and then I run it, and look at that, 0, 1, 0, 1. Now, what I also want to show you is that instead of using binary, which is zeros and ones, I can put an X, and it will use hexadecimal. So like if I say 9, and run it, what do I get? I get an 8 and a 1 makes a 9. Well, what is 10 in hexadecimal? That's A, okay? And then I run an A, and what do I get? 1, 0, 1, 0, which is 8 plus 2, which is 10. Okay, let's see if we can get some questions here. You guys, if you have some questions, let me know, and then we'll just play around with this program a little bit more. But as I'm waiting for some questions, what I want to show you is you define the state machine here. Like, why am I going 2000 hertz? Because if I try to blink this thing, I want you to see it. I could make it, if I wanted to go fast, 100 megahertz. And at 100 megahertz, what would that mean? Each command would take exactly 0.01 microseconds or exactly 10 nanoseconds to execute. And I have absolute control of that. So right now at 2000 hertz, each command takes half a millisecond. This would be exactly half a millisecond, exactly half a millisecond. And the wrap and the wrap target are not commands. And so to do this, it's going to be doing it, the whole program is going to be looping at a total of 1 millisecond. Okay, how was it hexadecimal? Well, when you put the X here, that is telling that you have the data type hexadecimal. How does hexadecimal count? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then A, B, C, D, E, and then it wraps back around to 1, 0, which would then be the next number. Okay, so that X is what cues it in that is hexadecimal. In line 8, where is the pins defined? Well, the pins are the pins. What are the pins? The pins start at pin 16, and there are 4 of them. So it is pin 16, 17, 18, 19. I could not make it 16, 18, 20, 22. All right, the pins are defined. The base pin is defined here, and then how many pins you have are defined here. Did that answer your question? Okay, I see base 16. Okay, hexadecimal is base 16. Yeah, okay, yeah. Okay, you understand now. Okay, so what other questions do you have before we try to do a few more things here? What other questions do you have before we try to do some more things here? Okay, you guys, please ask some questions. I'm worried that maybe I'm doing something that you guys aren't interested in. Okay, let's, so I can do a 0XA, or let's just come back and let's make this a 0B and then a 1010 like that. Okay, and so then I can run it just to make sure, and yeah, I've got the 1010 there just like I would expect. What is the purpose of state machines? Is it processing efficiency? Of course. No, it is when you need precise timing. So like if I need exactly a 10 microsecond pulse, you can write a program in Python or MicroPython that will tell it to make a 10 microsecond pulse, but what you'll get is anywhere between 30 and 80 microseconds, because you don't have precision control of timing when you're in Python and using the main course. There's too much other stuff going on. Okay, is it impossible to use any other pins? Well, I can use any, like I could say I want to start at pin 0 and I want to use 16 pins, and then the pins would be 0, 1, 2, 3, 4 up through 15. You see, so I can define any set of pins I want, but I just defined the starting pin and how many pins there are. I can't randomly select different pins. Just can't do it, can't do it, can't do it. Okay, I'd like to make a simple counter in the state machine, then use Python to periodically look. Yeah. And that's one of the first few lessons we'll do, is starting to do counting and timing type things in this. Okay, if a pin is used by a state machine, can you use it in Python program also? Man, that could get pretty confusing, couldn't it? And I think you would probably end up with timing problems because it would be very hard to synchronize that. So personally, if I was working with a pin on the state machine, I would work with it in the state machine, and then I would send that from the state machine to Python, and Python could send a query, and then the state machine could do something and send it back. But if the state machine is between the Python and the GPIO pins, I wouldn't try to go around the state machine. But that was a good question. I'm not sure on the 2350 about what they've done or haven't. Hey, Arnold got his working good. What might be some practical project applications that would require precise timing? Well, anything that you might want to do with something like PWM, right? PWM will create a series of exact time pulses. But what's the problem? What's the problem is it's repetitive. What if I wanted a one-shot exact 10 microsecond pulse? You can't do that with PWM. What do you need to do that with? You need to do that with the state machine. Or if you wanted to have a communication protocol with different components that require exact timing, you would need to use it. Or if you just want to offload some of the interaction with the GPIO pin so that you're not using up resources on your main Python program. So let's say I had a GPS. I could set up the state machine to be pulling the data from the GPS, forming the NEMA sentence, and then sending that NEMA sentence back to Python. And then Python could just be doing all of its stuff, and the actual gathering of the data could be done by the state machine. Okay, I heard that on another video today that sleep timing wasn't perfect. Jason, it's worse than not perfect. It's really horrible. And when you hook it up to a oscilloscope, what you see is it's not only off, but it's off randomly. Maybe it's too short, maybe it's too long. You never know what you're going to get. Now, if you're saying every 10 seconds make a temperature measurement, that doesn't really matter. But if every 5 microseconds you need to get a bit from your GPS unit, all of a sudden timing becomes very, very important. Okay? Yes, Peter, you're exactly right. One of the great things that you can do with the state machines is it's a great way to interact with NeoPixels. And so that is indeed true. Okay, well, if we set this, if we turn those on, what if we tried to blink? So what if I said set? How would I blink it? Well, now I could come in and I could set X again. I could say this time set X to 0B. And this time I want to go 0, 1, 0, 1, like that. Set X to 0, 1, 0, 1. Now what do I want to do? I want to move to the pins what is in X. And now, what do you guys predict is going to happen now? So I set it to 1, 0, 1, 0. And then I move it to X. I set it to 0, 1, 0, 1. And then I move it to X. And then I wrap. What's going to happen now? See if any of you guys can give me a guess what's going to happen now. Man, you're a very quiet crowd today. You're a very quiet crowd. Okay, well, what you might guess is, you might guess that it's going to blink. Okay, so let's run this and see what is going, the alt lights, the alt blinks the lights, every other will blink. Yep, so let's run this. And what do we see? It seems like it turned all 4 on. Now, why does it look like it turned all 4 on? What was the slowest that I could operate at? The slowest that I could operate at was 2000 Hertz. That means it's on for half a millisecond, off for half a millisecond. Now, what is wrong with that? Remember when we did those old first programs on Arduino or Raspberry Pi Pico? Remember that you had to have kind of like 16 milliseconds on and off to be able to perceive blinking. So this is blinking like 50 times faster than what your eye could see. So let's see if we can slow it up a little bit. Okay, let's see if we can slow it up. What I can do here is I can put sort of a pause in here. I can say set X to 0B 1010, and then I can say pause for 31 clock cycles. So it's going to do the command, and then it's going to do nothing, do nothing, do nothing, do nothing for 31 clock cycles. So this line of code does 32 clock cycles and 1 command. Well, I can come here and I can say do this command, and I can say then sit for 31 clock cycles, do this command and sit for 31 clock cycles, and then do this command and sit for 31 clock cycles. And this isn't costing me any more resources because I haven't added any lines of code. It's just going to sit at those for more cycles. Now, why don't I do it for wrap and target? Because those are not commands. Those are not commands. Those are just labels in the memory that it then jumps to. Okay, so now let's see if we run this. And what you can see is, like, with my eye looking at it directly, I can see that it's doing it, and it's doing it perfectly smoothly. The reason on the camera you see a little pulsing is the camera has a certain shutter speed, and then that's not syncing perfectly with the LED. But when you look at it with your naked eye, then you can see it perfectly. But you would really like to slow it down more. So what I could do is, after I turn those on, I can do a new command, and that new command is no op, and no op does nothing. Okay, and how many times do I want to do no op? I want to do no op once, and then 31 pauses. Okay, and then let's do no op. Okay, and then 31 pauses, and then let's do no op, and then 31 empty cycles, and then no op, and then 31. So let's see, I've got like 32, I'm at a half a milliseconds, and so 32 of half a milliseconds would be, kind of like 16 milliseconds. So I'm starting to get something that I might be able to perceive. Now I'm going to take those 4, I'm going to copy them. I better put a space in there. I'm going to take those 4 and I'm going to copy them. And then after this, I'm going to paste them. And now let's see if we can slow that down a little bit. Okay, so we're going to do it. Yeah, now I can perceivably see that I have slowed that down. So let's go again. What if I get these and I copy all 4 and then I paste? Okay, and then I come up here and I paste. And now I've kind of doubled the amount of empty cycles. Okay, there you can really start seeing it. Now what if I want to do that again? Okay, what if I want to do that again to slow it down further? I'll put 4 more, and then I'll come here and I'll put 4 more. And now let's run it. And now look at that. That's really, you can very much perceive it. So I'm going to do it one more time. I'm going to Control V for 4 more. Okay. And then I am going to up here, I'm going to Control V for 4 more. Okay. And now let's run it. And denied. OS error. Error number 12. ENOMEM. MEM makes you think of what? Makes you think of memory. What happens? How many lines of code can we have? 32. And we just went over our limit of 32 lines of code, and so the program crashed. So let's see if I take 2 out here, and then let's see. I didn't keep track of my lines of code. Okay, 2 here. And now let's see if that will run. Okay, still too many. Let me take out 1 more and 1 more. Boom. Okay, so you see this is the slowest that we could run it because we're operating at the slowest clock speed, and I put in as many delays as I could. So what do you see? When you are programming and only have 8 commands and only have 32 lines of code, you've got to be smarter than what I just did. You can't afford to use like 28 lines of code just to generate a delay. You've got to go in and you've got to think, how can I use those 8 commands I have to make something that would, how can I use those 8 commands that I have to make something that would delay using much fewer, that would delay using much fewer lines of code. And so those are the things that we're going to be doing when we get into that. Now that's cool. Can you increase more than 31 cycles? No, I mean, this is 31 plus 1 is 32. That's all I can do in 1 line of code. You see, if I made this 36, the program's going to crash or it's going to have an unexpected result. Could you use the jump command to loop? Very good. But you would have to understand the jump command. You would have to build into the jump command a counter so that it wouldn't just jump forever. But you're on the right track there, Daryl. That's very good. Why are there more than 32 lines in the program? Is there more than 32? Let's see. Remember, when you say that, wrap target is not a command and wrap is not a command. So let's see. It looks like that I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, I've got 15 here and 15 here would be 30. And then what you have to see is I've got 31. This, I don't know, what is that one doing down there? That's kind of an odd place to put it. But this wrap and this wrap target, those are not, the wrap and the wrap target are not commands. I kind of got a strange thing here. Okay, this set down here is sort of that doesn't do anything because when you come up here, you're setting it again. So this command down here, I don't know how I ended up with that there. And here we set it, and then here we move it. So that looks good like that. Hopefully that answers your question. It's the code moving around the state machine. Okay, why are there's not? All right, Larry's got that. Could you use the jump? Yes. Could you increase? No, you can't. Too many lines. Yes, you got it. You pasted it. Oh, okay. Yeah, Mark. So when I cut and pasted, I accidentally cut that line of code. All right. Okay, so you can see that's pretty interesting. Let me come over here. Like, this is one of the things that I'm gonna show you that we're gonna start doing is like, okay, now just with 32 lines of code and you can't do addition, subtraction, multiplication, and division, but then this is one of the things that I did. Okay, this is a program that I wrote and it's solely in the state machine. Python isn't doing anything at all. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 0, 0, 1, 2, 3. So I made a binary counter in the state machine, and I don't have add, subtract, multiply, or divide. So you see, you gotta really think. And look at this, it's going very slow where you can see it. So I had to have a clever way of putting a delay in there. So you see, that is what we're going to be, that's what we're going to be doing over the course. That's what we're going to be doing over the course of the next probably 10 classes or so in the Raspberry Pi Pico W class, is really going in and learning how to use the state machines and doing some fun or cool things with those. So let me stop and let me see what you guys think. You guys give me some feedback. This has been a very, very quiet group of people this morning, and the great thing about the live chats is the interaction. So come on, you guys, let me know what you think. Give me some questions. Hey, Michael, it's been a long time. Welcome back. Haven't heard from you in a long time. Glad to have you here. So you guys, throw me some questions about this or what we're going to be doing on the channel in the future. Let's just take a few minutes here to have a little interaction with you guys. I don't know if you're just very quiet today, or if maybe there's a little more latency in our connection. I like it. Got to think about using it. Okay, good. Lee says very cool. All right. Now I might buy a Pico and try to catch up on this feed. Guys, man, I'm doing the class on the Arduino and I'm doing the class on the Pico. The more I use the Pico, the more I really, really love it. And if I were personally going to go out and do a project on something like just a personal interest thing, the Pico would be the platform that I would buy. And so Arduino was our first single board computer, and it'll always be special to us. But man, I'll tell you, there's some really great things here about the Arduino was first, but there's some great things about the Pico. Okay. Hope you're well. Yeah, I'm doing great. This is super cool. BBF says, yeah, it is really, really fast. The maximum speed is 133 megahertz. So that would be like 10 nanoseconds per operation, per line of code. Can't type code and chat at the same time. Okay, Arnold, I understand that. It's going to be very complex. Well, it can't be that complex because you've only got 32 lines of code. It's like 32 lines of code. Use them wisely. You must use them wisely. Can you use bit shift operator? Hey, Quaternion, welcome. Not sort of. I can scoot something in that will scoot the other things out. So with like the out and in, it scoots them in. And you can do that in a way that's kind of tricky. Okay, so that was a good question. Let's see. Arduino not completed, but you started. Okay, good. Closed loop control for encoders with PIO would be nifty. Absolutely, David. Arduino not completed, but you started advanced. Arduino. Okay, yes, we hear you, Neem. Just wanted to say I appreciate what you do. Hey, Jo, appreciate that. Great to hear from you. Okay, yes, Neem, we've heard you. We've heard you. Thank you. Okay, so anyway, that is where we are going. Let's see what we've got here on the stream. Yep, it looks like the sun is up outside. Beautiful morning here at the headwaters of the Nile. And so love to see that every morning with my coffee. So anyway, guys, that is where we are going in this class. That is where we are going. And I hope you guys that are not doing the Pico lessons will go ahead and get yourself a Pico and start working on these things. And then I've got just some really, really exciting things that I have in mind that we're going to be doing with the Pico. So anyway, we're just 3 minutes over an hour, and I like to try to not make these things run over an hour. I appreciate you guys tuning in, and I appreciate your participation in the channel. But I think now I'm going to go ahead and wrap this up. So what I will say is appreciate you tuning in. Hope to see you guys next week on the classes that we'll be having. Paul McWhorter with TopTechBoy.com. I will talk to you guys later.